Hey there, welcome back. And today we're going to be talking about electric potential part two, and that will be the content of tomorrow's lecture. So, this is in a way partially a review of what we saw in electric potential part one, but with a few more details. So, remember that the electrical force is defined between 2 point charges. And so, if you have these 2 point charges, Q1 and Q2, then the magnitude of the force is a constant times the magnitude of Q1, magnitude of Q2, divided by the distance between them, between the two charges, squared. And this force will be repulsive or attractive depending on whether the forces, on whether the charges are of the same sign or of different signs. And of course, the force is a vector, and so this is the magnitude of that vector. But what about the direction? Well, that depends on whether the force is attractive or repulsive, but it will be along the line that joins the two charges. So for example, if these two charges are of opposite signs, then the force on Q2 due to Q1 is going to have this magnitude and it's going to be pointed towards Q1. Okay, similarly, if the charges were repulsive, if the charges were the same sign, so the force will be repulsive, then the force on Q2 due to Q1 would be along the line that joins the charges, but it would be pointed away from it. And this would be, again, the magnitude of the force. So that completely determines the vector. So we have the magnitude and the direction. Now, to help us with understanding force, in particular action at a distance, we defined what we call the electric field. And so this field is defined entirely with a single charge. You don't need a pair of charges to define the field. And we say that the electric field due to a charge Q, depicted here, has this magnitude. So the electric field has the magnitude K times magnitude of Q divided by R squared, where this R is the distance to the observation point. So this field, and this is what it means to have a field, is something that exists everywhere in space. And so this charge Q generates this field everywhere in space, and the magnitude and direction of the field is determined then by, well, the magnitude is determined by this formula, and the direction is determined by whether the charge is positive or negative. So if the charge is positive, the field is away from the charge, along the line joining the charge and the observation point, away from the charge if it's positive, and toward the charge if it's negative. So that determines then the electric field. And here I drew it only at one point, but this field exists everywhere, and it's induced then by the existence of this charge at this particular point. Now, since we talk about forces, there is a potential energy associated with electrical force. And once again, for a pair of particles, the energy, the potential energy associated with the electrical force between these two particles is given by this formula. So it's given by the constant K that we defined before times Q1 times Q2 divided by R, not R squared, but R. This is very important. And so then this is the electrical potential energy due to the interaction between these two charges. Notice how when we talk about force, we use a pair of charges and it goes like 1 over R squared. And then when we talk about potential energy, once again, we talk about a pair of charges and then we divide by R, not by R squared. The potential energy could be defined for systems of more particles, by the way, but it's always pairwise, okay? So that means that if you had a third particle over here that is charged, then you have an interaction between Q1 and Q, let's call it Q3, then Q2 and Q3, and Q1 and Q2. So this electrical potential energy would have three terms, and you have to calculate this for each pair of charges. So 1 with 2, 2 with 3, and 3 with 1. Okay, so that's if you have more than two particles. And so this pairwise expression then defines everything you need for any number of particles. So just go with pairwise interactions. And by the way, if you have the one between 1 and 2, you don't need to consider the one between 2 and 1. That would be double counting. And so you have 1 and 2, 2 and 3, and 3 and 1, like I said before. Now, to help us with electrical potential energy, actually, it's useful to define something called the electric potential. And this is important to distinguish from the potential energy. The electric potential is, if you want, the analog of the electric field, but now for energy instead of for the force. This electric potential is defined entirely due to a single charge Q, and this expression here, and it's a scalar. It's just a number. It's the constant K times the charge divided by R. And so what is this R? It's once again the distance to the observation point. But now we don't have a vector as we had here, this electric potential is a scalar, and in reality, it's a scalar field. So again, this potential exists everywhere in space, everywhere around this charge, and its value depends on this expression, kq divided by r. So it depends on how close you are to the charge. And so then we say that the presence of this charge q creates an electric field, and also associated with it a potential v, which, as I said before, is also a field, but it's a scalar. It's not a vector field, it's a scalar field. This is useful. These fields affect the motion of other charged objects. So E, the electric field E, is a vector. It helps us calculate and imagine forces. And in other words, if you go up here and you think about the influence that this charge has in all of space, then if some charge from far away comes into close proximity to this charge, or even if it's a little bit away, it will always feel the electric field due to this charge. So that's the idea of electric field. And the same with the potential. A charge brought from far away will see the presence of this charge by virtue of its potential, by virtue of having a non-vanishing potential somewhere in space. And this V will help us calculate the energy. So E helps us with forces, and V is what speaks to the energy. So let me give you an example here just to conclude. If you have a charge Q, let's say it's a big charge, 3 coulombs, sitting at a point where V is 2 volts, and this could be an example here. For example, this is a charge that generates a potential, and let's say at this point, the potential is 2 volts, and we bring a charge from far away that is 2 coulombs. Sorry, I said 3 coulombs and 2 volts. Okay, so suppose we have the 2 volts and 3 coulombs, and so if that's true, then the potential energy of this system of these two charges, or if you want, the potential energy of the system of the charge Q with whatever it is that generated these 2 volts, is given by this U, which is Q times V. So you just multiply these two things and you get 6 coulombs times volts, which is joules. So in the product of the charge that you brought in times the potential at that point where your new charge is sitting, that gives you the total potential energy of that system. And so we're going to be using this quite a bit. This is just a potential energy. Now, if your charge is also moving and has kinetic energy, then you have to add these two. And then you can think about considerations of conservation of energy. If the charge continues to move, and then at a different point, it may have a different kinetic energy. And so you can determine potential energy, or vice versa. If it moves from one potential to another potential, you can think about how the kinetic energy changes and how that is governed by conservation of energy. You've solved many problems on conservation of energy before, so this is just going to be a different application of the same idea. And that's all I have for you today. I will see you tomorrow.